Hi everyone, I'm Aditya. I'm a PhD student here at Harvard in physics. And in my work, I study light. And I want to tell you in this talk about why light is not just a tool to see the world around us, but also has interesting properties by itself and has intrinsic features that are quite interesting to look at. So I'm going to talk about two different aspects of it. So one is introducing light as a wave. And it turns out light is not just a wave, but you can also think about it as particles, and I will talk a little bit about that as well. So light as a wave is more common, and that's, I think, what most people are familiar with, and that's what lets us see the world around us. But the wave nature of light results in the light beams forming interesting shapes that I will introduce later on. And light as particles are actually not that different from what you would imagine regular particles like atoms behaving, and they can form molecules and crystals, and I can tell you about how that happens. So when you see a picture like this or a scenery like this, there are a few key features here that light helps us see. So one thing is brightness, tells you how bright or dim or dark the picture is or the scenery is. And it also helps us distinguish colors. So on a beautiful fall day like this, you can see the different shades of leaf colors all the way from green to yellow, brown, and red. And let's see how light as a wave helps us see these different features. But before I get into that, let me just quickly give you an overview of some wave physics. So a wave is something that's oscillating in space and time. And these waves have some key properties. And waves are all around us in nature. The sound waves that are coming from these speakers into your ears is what helps you hear what I'm talking about right now. You can see waves in ponds and like surfaces of water. The ripples in water are also waves. And stringed instruments like a guitar, when you pluck the string oscillates, and that's also a wave. But in this context, I'm going to talk about light as a wave. So one feature of a wave is its amplitude. It tells you how high up and down it's going and oscillating. And another feature of a wave is its repetition time. It tells you how fast does it come back as it's oscillating. This is related to the frequency. Frequency is just the inverse of this repetition time. So higher the frequency, the faster it's oscillating. The lower the frequency, the slower it's oscillating. So when you combine this to see how it helps us see things, the amplitude corresponds to how bright things are. So something that has a higher amplitude is brighter, and something that has a lower amplitude is dimmer. And frequency helps us see color. So something that's oscillating slowly will appear red to us, and something that's oscillating really fast will appear blue to us. So depending on the frequency, we can see different colors all the way from red, yellow, green, all the way up to blue. But these are just two properties. There are actually more properties of light that can be harnessed to look at the world around us. And these other properties helps us visualize these 3D objects, and that's what allows us to create these things called holograms, which are a reconstruction of an image using laser beams. So you see kind of a laser beam forming a 3D object in front of you. Or also the other properties of light that helps us see 3D images. So if you've seen 3D movies and 3D TVs where you wear these special 3D glasses to look at them, you use a special property that we'll talk about to see the 3D nature of the picture. So one property of light that helps us see 3D information is the phase of light. So if you look at the solid wave versus the dashed wave, you can see that they have the same amplitude and the same frequency. The only thing that's different between them is really the starting value. So the dashed one starts at a higher value than the solid one. And this information in the phase can encode the 3D nature of an image and help you create holograms like this, where you can actually reconstruct not just a picture, but actually the full 3D structure of the object. And another feature of light is called polarization. Polarization tells you which direction the light is oscillating, whether it's going up and down or left and right. And this information in the polarization of light can be used to store, again, 3D information in an image. So when you see an image like this, and if you put on these 3D glasses, your left eye and your right eye are seeing different polarizations, and helps you actually see an image that looks like 3D. So that's how, when you look at a 3D TV or a 3D movie, and when you go to the movies and wear these glasses, you get this depth perception. So far, I've talked about how you can use all these different features of the wave nature of light to look at the world around us. And it's an amazing tool. It lets us see so many different things. But what I'm going to talk about now is trying to tell you that this wave nature can by itself have some interesting properties. It's not just looking at some third object, but itself can result in some interesting shapes. Have any of you been inside an infinity room, like a room that looks like this before? It's amazing. I always, when I go in there, I really get confused because I see multiple images of myself and I just go crashing into the mirror all the time. So an infinity room, for those of you who've never been into one before, is basically a room where all the walls and the ceiling and the floor are covered in mirrors. So what happens is that one of them creates an image, and then the one behind it creates an image of the image, and this goes on forever, and then you see multiple reflections of yourself in all directions, and creating what is like an infinity versions of yourself, or whatever is placed inside. So that's why it's called an infinity room. So the important feature that I'm going to take away from this is that when you have two mirrors that are placed back to back, the light beam can reflect back and forth between this forever. But if you think about light as a wave, what's happening is that the light wave is moving forward and then backward and then so on and so forth. And these light waves can start interfering with one another. So let me talk a little bit about what it means for waves to interfere with one another. So there are two extreme cases. So one case is, let's say we take two waves and they add together and then they superimpose and becomes twice as big. So that's called constructive interference, where they add up and then become bigger. And the other limit is when the beams don't add up together, but they cancel out, and then you have two waves that add up and then you just get nothing out. And that's the complete opposite limit, so that's destructive interference. And you could have usually a gradient in between, where you could have somewhere in between constructive and destructive interference. So when you have these two mirrors where light is bouncing back and forth between them and it's interfering with one another, if you wanted to go on in perpetuity, you want it to constructively interfere, because if it destructively interferes, then it just will die out over time. So it turns out that there are only certain shapes of light that, as it goes back and forth in this mirror, will survive and have this constructive interference. And these shapes are like the ones that you see here, have these like very nice geometrical patterns that form. So you see this nice circular feature, or you see this like two-lobe dumbbell-shaped kind of feature, or the three-lobed, or 4, 5, 6, and it keeps going on and on and on. But there are only these special kind of shapes that, as it reflects through these mirrors back and forth, come back to its same shape and have constructive interference. So the wave nature of light, through this interference process, results in its forming these kind of beautiful geometrical shapes. So tying all this together, light as waves is wonderful as a tool to see things around us, pictures, objects, and sceneries around us, but can also, through this interference pattern, can result in these geometrical shapes forming in special scenarios. So far I've talked a lot about what the consequences are of having light as a wave. But it turns out you can also think about light not just being as a wave, but also as a particle. And this particle, like I was saying before, is not that different from regular particles like atoms, but it of course has very key differences from atoms. These particles of light are called photons, and I'm going to use the word photons from now on. Photons, unlike regular particles which can stay at rest, are moving really, really, really fast. So they don't interact with one another, and they move so fast that they disappear in the blink of an eye. So to give you a sense of how fast it's moving, it can traverse your body length up and down 1 billion times in 1 second. So it's moving extremely fast. So to make these light particles interact, we need to slow them down. And slowing them down, it in ways works similar to what happens, say, when you try to run on a nice track versus trying to run in water. When you have stuff around you, it's much harder to run fast. In a very similar way, when you put these photons inside a medium where there's a lot of stuff around, these photons bounce off these different particles and then try and become much slower. So once we put them inside such a medium, they go much, much slower, and we can engineer the interaction. And one kind of interaction that we can engineer between them is making them attract one another. So we can have two photons that pull towards each other. So we can have two photons that over time slowly come towards one another. And this can be quite interesting because, as you can imagine, when two atoms, for example, attract one another and come together, they can bind together to form a molecule. And in a very similar way, we can get these photons which are attracting one another to bind together to form a photon molecule. So what you're looking at here is the likelihood of photons arriving together, and these yellow lines represent two photons arriving together, and they indicate the presence of a two-photon molecule. And right in the middle, where you see this red dot, is a much higher probability of photons arriving together, which indicates the existence of three-photon molecules. So through this attractive process, we can get photons to bind together to form molecules just like regular atom does, and form this exotic state of like light matter. And we can engineer not just attractive interactions between them, but we can also make the photons push each other away and have them be repulsive. And so when you have two photons next to each other, they can push each other away and go further out from each other. So you can imagine that suppose things are pushing each other away, it can result in an interesting feature where I can give you a simple example where, let's say you have a bunch of people in a room, it's a closed room, and each one's trying to push each other away. And so everyone's in the middle, and each one's pushing each other away, and then they want to be as far away from each other as possible. So each one is at an arm's length away from everyone else. And you can see if they do that, then they will self-organize to form a periodic or crystal-like pattern where everyone is an arm's length away from everyone else. And this is what photons will do too. Is if you have a bunch of photons and they're all pushing each other away, they will self-organize to form a crystal. So in the graph here again shows the likelihood of photons being together, and you see this kind of oscillatory behavior starting to appear, which means that the photons are now forming a periodic pattern in space. And so through these repulsive interactions, we can create this new exotic state of light matter, which is a crystal of photons. So through these particle-like behavior of photons, we can make them sort of matter-like and have them bind together to form molecules, or have them push each other away and form crystals. And tying it all together, so this is the particle side of light, but also even the wave side of light allows us to create these, through this interference, these interesting shapes. And I hope through this small talk I've been able to convince you that light is not just a tool to see everything around us, but also has interesting properties by itself that are just intrinsic to the properties of the wave nature and the particle nature of light. And with that, I'd like to thank you for your attention.
So we have time for some questions, if anybody has questions for Aditya about the exotic states of light.
Yeah.
What would cause two photons to attract or repel each other? You know, you can think about electrical positive, negative. So
Yeah.
What's going on there that causes attraction repulsion?
Right, so what's actually happening is that we are slowing down these photons by mixing them with some other atoms, and then the interaction is sort of induced from the atomic interactions. So whatever the nature of interaction the atom has is induced into the photons, and we can control that by changing that mixing. So we can either make it attract or repel depending on what the atom does.
When I think you call those cavities or something, the one where you had the geometrical, like the duo, trios and so forth.
Yeah.
Was that the result of the mirrors against each other, or was that starting? You said something about two things. Some things will do that and some won't. The simple structures will reflect back.
Right. So
I mean, was that the result of things reflecting against each other, or was that the start?
So that's the effect of the light beam interfering with each other as it's reflecting back and forth. So this is what forms as it reflects over time.
So that would be the result.
Right, exactly.
Could you just explain a little bit what specific crystal patterns, what like crystal lattices or?
So all of the photons in this case are identical, so it will just be a lattice where you have equally spaced photons from each other in a line.
Like one-dimensional line? In
a one-dimensional line, they're just equally spaced.
Okay, so we're going to move on to the next talk, but Aditya will be around at lunch and you can ask all the questions then. So let's thank him again.